Okay, so I'm just going to jump into this because I timed this and it takes about an hour. So I'm just going to go for it. Yeah. Okay. So yeah. So I'm just going to jump into this because there's a lot about systems philosophy. Marty said something to me the other day. He said, I came to a systems thing 30 years ago, and he said things haven't changed. And there's some sense of that. I wrote a paper in 1978. It was based on a talk I gave at Brunel University, the Cybernetics Society, and about the problem of the relationship between systems theory and philosophy. And it's still there. Anyway, so my background, very briefly, I started out in philosophy of science. These are kind of my mentors, Berkeley, and I went to London. And my dissatisfaction with philosophy of science, these guys are all rebels, so I was aligning with them. And I didn't like the philosophy of science. I didn't the dominant philosophy of science, and I didn't like the scientific worldview. I thought it was a lot of nonsense. And gradually I morphed over into philosophy of engineering. And actually I was sort of already there, but I didn't know it at the time, which I'll explain to you. I've written a little bit about this, and basically the contention is of looking for an engineering worldview, engineering philosophy and philosophy of engineering, philosophy, engineering, and engineering worldview. And what I want is I want a bigger tent. Science I don't like because it tends to be deterministic, and I don't see myself in the scientific world, and that troubles me. So the formal thing is I want to, for a larger worldview, if you can paradigm shift, the two words are subsume and supersede. Subsume means that this new worldview, this engineering worldview, will be able to explain everything that goes on in science. Okay? Supersede is more subtle. Supersede means that the engineering worldview is actually more sophisticated and conceptually more sophisticated, and what we have understood as science, we maybe are going to understand it in a new way. Okay? So the paradigm shift here, most of Kuhn's paradigms were understood as being within science. So what I'm suggesting is a paradigm shift beyond science. Okay. And my hypothesis, so to speak, is so philosophy of engineering and systems philosophy are actually the same thing, which I will try and justify to you here. They're both what I call post-scientific, conceptually more general, sophisticated. And they subsume and supersede all possible deterministic scientific or mechanical theories. Now, a simple example of superseding is, okay, I had the flat Earth theory, we go to the spherical Earth theory. The spherical theory is more general. I'm able to understand why people believe the flat Earth theory. Flat Earth theory still works, great. And, I say, hey, well, I can understand why you believe that because we actually are very, very small people on this very, very large sphere, so flat works good, and it still works. Another example is in going the Apollo project to the moon, we did it all with Newton's theory because the relativistic correction is only 9 miles. We weren't even close to being that accurate with our burns. So it's not saying it's not going to work. Science still works. Science is good. Those relationships are good. It's just that you need to understand them in a bigger picture. And another thing is new questions, new novel questions arise, are possible, qualitatively new questions, arise in the more general theory. So here I can launch satellites, all sorts of things about Coriolis effects and stuff like that simply don't come up in the flat Earth theory. Okay, so a big question in a lot of this, and I'm going to come back to this a lot, is what are the relations between systems theory and classical ideas of science, mechanics in particular? So in general, I'm going to say that all the mechanical theories at work are all bounded, and they're special cases. They're bounded by boundary conditions and methods that are used. Now, and they're valid, and they work within, I think what was one of the guys going to a domain of validity. They have a domain of validity defined by those. And the other thing that's general of all mechanical theories is they all assume a symmetry and they all assume conservation of something, usually energy in these days. So hypothesis is the philosophy of engineering and engineering worldview is the systems philosophy and is the systems worldview. I want to make a distinction here now between there are two different approaches in what is knowledge and what is the whole thing. So one is a spectator view. So like there's this objective world out there and I'm the scientist and I'm somehow getting this information, but I'm not influencing that thing at all because if I'm influencing it, then I'm probably not able to tell the factor of my influence. So the spectator view is tends to be science. I'm looking for the universal laws governing the world out there. and I'm not interacting with it. I'm not part of the world. I'm just, I'm an abstract scientist looking for the theory of everything. And the systems engineering is a participant framework. Engineers are part of the world. They're agents, embedded components of the world. So this people wondering about where the systems philosophy is. It's been around a long time, folks. Pragmatism is a system philosophy, always has been. Anyway, this spectator participant thing is really pushed by John Dewey a long time ago, and different ideas of knowledge and so forth come out of this, which I'll go into. Now, the idea that that we're agents in the world, I mean, scientists have a problem with this. Free will? What do you mean free will? It's ridiculous. So this Steve Weinberg says, isn't it quaint that engineers think that they can change the course of events and restructure reality? Because we physicists know that there are these universal laws that determine everything from beginning of time forward. Engineers are like, give me a break. So I love this Stephen Hawking, see him with some kids with disabilities at a thing we organized for him. He has this great talk. I've noticed that even people who claim everything is predestined, that they can do nothing and that they can do nothing to change it, look before they cross the street, cross the road. Okay, and another guy I thought was good, just people who are promoting determinism or scientific worldviews, if you like, have lost touch with common sense. Okay, so one of the seminal publications in this agenda that my colleagues, is a book by Walter Vincenti called What Engineers Know and How They Know It. I recommend it to everybody. So what Vincenti says is like, look, you got any epistemology, he's talking about knowledge and stuff. He says modern engineers are seen as taking over their knowledge from scientists, and by some occasionally dramatic but probably intellectually uninteresting process, use this knowledge to fashion some material artifacts. Okay, it says from this point of view, studying the epistemology of science would automatically subsume the knowledge content of engineering. Okay, so engineering is within science, supposedly. And he says, engineers know from experience this is not true. He says, from an engineering point of view, technology appears not as a derivative from science, but as an autonomous body of knowledge. As Guy said, he's an aeronautical engineer, so he stays in aeronautical examples. Stanford guy. So airplanes are not designed by science, but by art. In spite of some pretense and humbug, the contrary, I do not mean to suggest for one moment that engineering can do without science. On the contrary, it stands on scientific foundations, but there is a big gap between scientific knowledge and the engineering product, which has to be bridged by the art of the engineer. The creative, constructive knowledge of the engineer is the knowledge needed to implement that art. Systems engineering knowledge is about how to do things in the world. It's about methods. This is all about pragmatism, too. It says, what are we learning? We're learning how to do things. So systems knowledge is about how to change the world, how to course of events, so forth. So the basic idea here, again, this subsumption, this superseding thing. So I'm saying is that real knowledge is engineering knowledge, okay? And science is going to fit in. I'll go into that a little bit more, but that's the basic idea. So engineering knowledge is much more sophisticated conceptually than the scientific knowledge based on symmetries and so forth. Nice tools, but we love the scientific tools, but they don't tell you how to build an airplane. They'll tell you how to build a smartphone. This is another publication I did on this stuff, so if you want to look at it. Okay, so part of the problem is so inquiry doesn't make. What I push here is that the very idea of inquiry doesn't make sense in a deterministic world. Okay, I don't know if anybody might still want to try and defend that sort of crap, but I mean, it's just, come on. I mean, what is a question in a deterministic world? There are no questions in a deterministic world. There are no people in it, and there are no scientists in the world. Okay, so if you don't have the freedom to test your hypotheses, you say, "Oh, I found out this." Well, if you can't test that, if you can't falsify it, if you can't figure out a way to do that, then you have no confidence at all in what you're learning. So if you say, oh, it's deterministic and all this, well, what confidence do you have in the knowledge that's all deterministically coming into your brain? Zip. So I call this Descartes' nightmare, because Descartes was concerned that God might be a deceiver, and then he just says, well, God's good, so he wouldn't do that. But here's the idea. If you get this deterministic view, what confidence do you have in the beliefs? Zero, okay, because you don't have a test. Okay, here's my favorite guy. see, inquiry is part of reality. So I call it, I got it from Royce, American Pragmatism. I call it Royce's criterion of self-referential coherence. Whatever view of the world you have, say, hey, I learned this is what the world is. Okay, you need, that worldview must have you in it learning about it, okay? Like, how did I learn it, okay? You must have learning in the world. So questions and learning must be essential, irreducible aspects of any self-referentially coherent theory of reality, okay? And he calls it the problem of problems. So he just says any theory of reality that you have must have problems and problem solving in it. And it must have agent problem solvers, which is learners. Okay, so we learn the world, stuff like that. But we can't, in the scientific world, there are no people. There are no learners. That process is not there. So learning and problem solving must be essential, irreducible aspects of the nature of reality. So goes the argument. Okay, so I'm saying you can do it. So one of these arguments. So if I can't understand, so I need this larger engineering view to understand what knowledge is. So what we're calling science, what we've been calling science, is really engineering. Okay, Henry Petrosky, who's I don't know, you guys know him, 24 books or something. He's an engineer at Duke University. He's read lots of stuff. Very good. In this book, he says, I put it my way. Everything you thought of as a science is really engineering, okay? And it's really saying this. It's saying everything you thought of as scientific inquiry is really engineering inquiry, packaged in a certain way about these domains and axiomizing the system and so forth. So, and this is a consequence of the idea that engineering knowledge is the bigger tent, and engineering knowledge is what's real, and scientific knowledge is some of these idealized, things that aren't really there. Okay, so the question now is according to this thing, how do systems evolve? I'm going to say quantum theory is the current, good guy in the world. And one thing in quantum theory is, one thing we know is that systems do not evolve mechanically, okay? Because we have too many mechanics. We have the particle mechanics, we have the wave mechanics. Well, how does it actually evolve? According to what? Well, it depends on, quantum theories become a participant theory, okay? The only way that we can determine from this, ambiguous situation of opportunity is that somebody's got to actualize that situation in one way or the other. So I want to say, engineering worldview is post-scientific, post-mechanical. So is quantum theory, and not too surprisingly, you'll see that they actually come together a bit. This is John Wheeler, who, when Einstein died, they said, who's going to be the Pope of science? And they said, oh, Wheeler. And she said, I will not wear the mantle of Einstein. But Feynman was one of his students, Kip Thorne, so forth. The guy was heavy duty. He was like a major guy. So he's very much of the idea that, you can't, unless you have observer, if you like, or an actor in the world to actualize that opportunity, you don't have any universe. You don't have any actuality. And he has a famous little picture of the, we're bringing the universe into existence, and you have to have actors in the world, or you don't have any world. Okay, and that's an implication of quantum theory that a lot of people went with it for a while, and they liked it. And they didn't know what the hell to do with it, so they sort of just kind of get rid of it. So he had a great article, if you want to read it. It's called, in some of his collections, Observership as Genesis. So what he's saying is that, the world comes into being through observership. Now I'm going to change that a little bit. I don't like just observers, because observers, if we're in the world of observers, we're actually actors, we're agents, okay? So if you're a participant, if you're an engineer, or if you want to be a participant in quantum theory, it's the choices that you make of how to actualize the potential, the opportunity that actually brings things about. The idea, the classical idea of scientist as detached observer, as a spectator, is kind of over. Actually, I have a quote on that. So this is Wolfgang Pauli, who's really pretty good. Says, in the new pattern of thought, he's one of the founders of quantum theory. So, in the new pattern of thought, we do not assume any longer the detached observer, occurring in the idealization of this classical type of theory. But an observer who is, by his indeterminable effects, creates a new situation theoretically described as a new state of the observed system. Okay, and I would say indeterminable effect means that you can't understand in terms of quantum theory what tells you why the observer chooses how the observer chooses. A more complicated question. So I was saying, this is a great one of the philosophy engineering guys from way back, Sam Florman. Great stuff he wrote, and a book called The Existential Pleasures of Engineering. Now the key thing about the quantum theory guys can't tell you how you made this choice. Neither can you. Tell somebody until after the fact. I can give them just why I decided to go this way or that way. But the existentialist, continental existentialist, has a great thing. So here I am. I'm instantiated in the world. I have the ability to act, but I don't need script. You know, continental guys are like, oh my God. Anxiety. I don't know what to do. What am I supposed to do? You know, am I being graded? You know, it's like, there's no script. There's nothing telling me what to do. How can I do it? So this is existential angst for them. For me, and I think for a lot of Americans, it's like, there's no script. There's nobody grading me. I have all this creative opportunity. This is exciting. That's what Florman did. He said, hey, this is cool. And what engineers do is there's all this creative stuff. They have all this opportunity to do wonderful things in the world. And that's really cool. So that's what they do. So that was this kind of deal. I mean, the image of this is Gibbs. So how can you have, so Gibbs free energy, if you guys are into that, Gibbs free energy, it says essentially, you're highly constrained in the Gibbs situation, but you also have free energy. You have the ability to do things. So this is not off the wall stuff. My only thing is that Gibbs free energy is complementary to Helmholtz free energy, so it's not objective. Okay, so in the stereotypical images of collapsing the wave function and stuff like that in quantum theory are really limited. In an engineering participant view, it's RD&D. It's research, development, and deployment. And I would add on to that from some of the talks this week is management afterwards. You deploy, you have to manage it too. So what the choices that the engineer is making and actualizing different potentials is in fact, it's inquiry. Every time you do something, there's a question. You don't know, is that going to work or it's not going to work, or it worked over here, does it work over there? So everything you do is also exploration and inquiry. Questions and actions are tied to each other. So anyway, in the detached thing, you're looking for facts, as if there were any facts that were there that were not flexible. And then in the other, you're looking for methods and policies, which is pragmatism. Okay, so the other thing is, what is engineering? Okay, one other thing is, what's the problem of engineering? The problem of science is discovery, some sort of objective thing. So, well, forget that, it's over. The real problem is the problem of design. In engineering, that's a typical way. There's a problem in design. Better, okay. So how do I design the irrigation in my fields? How do I design my house? How should I design my neighborhood? How should I design my city? How should we design our economy? Should we have patents or tariffs or anything? How should we design our political system? Well, at that point, you're Plato's Republic. Okay, so philosophy is all through systems questions like this, okay? How are we going to do this? How should we organize this? How should we do this? These are design questions, okay? Herb Simon has a nice deal. He says, so what is engineering problem solving? He said, well, engineering problem is a problem of design. But he said, engineering problem solving is how to move from a current state of affairs to a future, more desirable state of affairs. I mean, it's almost a tautology from saying problem to solution, The solution is like better. One of the things about better is it involves values. There's no values in the scientific worldview. There's just stuff, okay, despite David's more enlightened view. So the progressive innovative designs require, and also this is just a characteristic of the engineering world, progressive innovative designs require experiment and exploration. It's not going to drive what the next solution is. What's the next theory? You got to go out and find it. You got to figure it out. Some of you guys know this guy who I very much like. It's a kind of a meta question. So if we're trying to make the world better, trying to do stuff, how would we organize society? This is a step beyond Plato, if you like. Plato wants to know how to manage a society, or organize and manage it. Churchman's asking the question, wait a minute, I would change the title to the design of an innovating system. How do you design a society that's going to innovate more, that's going to maximize its ability to make the world better? Okay, so I'm going to go back to this, how do systems evolve? So this is my next, I'm going to say they evolve. So they evolve thermodynamically. So I would say they don't evolve mechanically, they evolve thermodynamically. So well, how's that going to work if thermodynamics is reducible to mechanics? Well, it's not. That's kind of the gig. So the bold hypothesis is systems engineering and the systems worldview is actually thermodynamics. Okay, so I want to remind you all that quantum theory is a thermodynamic theory. Started with Planck and black body radiation, and in fact that was an engineering enterprise. It was funded by the German electric light industry that wanted to optimize power and how much power do I put in, how much light do I get out. So it is. And I was talking to my friend Brian Greene, who you guys may know is a big physicist guy out of Columbia. I said, Brian, we really need to revise our theory. If we're going to have new physics, we have to revise our theory of thermodynamics. It's all thermodynamics. If you guys hadn't noticed, string theory is a theory of thermodynamics. Okay? The beta function is kind of thermodynamics. Okay, this is a light interlude here. I was like talking to people about the worst course they took in college. Thermodynamics. You get through it, but a lot of things just don't make sense. These are the things that bother me. Like pistons that move infinitely slowly. I mean, what are we saying here? Is that a meaningful statement or not? Okay. There's another one. Lisa had invented a perpetual motion thing. You understand? Anyway, so, and partly I want to understand, I really appreciate this talk a couple of days ago by Bill Schindler, because what he did is he said, here's the deal. If there is a systems philosophy, a scientific basis for systems philosophy, and it's Hamilton's principle, okay? And he goes through that, and Noether's theorem and all that sort of stuff. And he makes a really good case for that. I'm going to say, if the universe was mechanical, he's absolutely right. That's the right place. But it goes focus back. I talked to Bill for probably an hour about these things. So where does Hamilton's principle come from? Well, Hamilton comes from Lagrange. Lagrange comes from Maupertuis. I'm going to. Another thing just to point out, this is Jeff West, he's a president of Santa Fe Institute for a while. He was the head of Los Alamos particle physics for a long time. So one thing he says, all the laws of physics can be derived from the principle of least action, which roughly speaking states that all the possible configurations of a system that can have or that can follow as it evolves in time, the one that is physically realized is the one with minimum action. Okay, and what we mean by action is a question mark. So he's saying, and this would go along with what Schindler's trying to push, really, and that is, consequently, the dynamic structures and time evolution of the universe since the Big Bang, everything from black holes and satellite transmitting your cell phone messages, cell phones themselves, all electrons, photons, Higgs particle, much everything else that is physical and determined by such an optimizing principle. And the optimizing principle is going to be the operational thinker. So as I talked to Bill, I said, okay, where Lagrange came from, and Ed, I'm probably going to run into the question period, so get over it. So anyway, you can ask me questions afterwards. There's no speaker after me either, so if people want to leave, that's okay. So anyway, so the optimizing principle is the key thing. So where did the principle of least action come from? It came to this guy, Maupertuis. And there's some argument whether Leibniz had it earlier or whatever. But there was this debate at the time, and it was like, what is conserved in motion? One was, well, it's momentum, it's mv, and the other one is mv squared, and I won't go the whole thing. But anyway, so each one of these, the mv thing has a conservation thing in it, and a symmetry principle. It's conservation, symmetry principle, and mv squared has conservation and symmetry principle, okay? But they're not compatible. They're not, which one's right, okay? You can't, derive one from the other as it goes. So Maupertuis comes up, and there's a whole war, and it's like Newton versus Leibniz, and the British versus the continental people, and it's like, I tell you, it's still going on, embarrassingly. But Maupertuis says both. Now the thing is the catch in all this is these are actually complementary frames. It's sort of like saying, if I'm observing in a phenomena, you and I are both on the same platform at the train station, and we're talking and we're observing each other. That's one frame. If one of us is on the train going by or accelerating going by, that's another frame, okay? Those frames are not one reducible to the other. Okay, that's basic what he's saying. So you got these two things. And then he says, and this is a problem that was very big at the time, and basically they're trying to figure, this is what Leibniz says, there are actually two components of motion. One is a kind of linear motion, and the other is this gravitational thing, okay? You can see it in orbits, of the planets, okay? There's like, if there was no gravity, the planet would just keep going, And if there was it didn't have anything like that, it would just be drawn into the sun. So the orbit is an optimization of these two motions. And what the big thing that came up, the Fermat has a whole history of this. Fermat had stuff. So the question is, what is the shortest distance between point A and point B? And you say, it's a straight line. Well, it turns out the shortest time is not the straight line. The shortest time, because you got this accelerating gravity, the shortest time is actually the red line, okay? And it turned out, there's a brachiochrome problem that everybody worked on it. It turns out that it's also a cycloid. It's a very interesting optimizing deal. Okay, that's the idealization, of course. So Maupertuis goes on, he says, look, everything in the universe, not just orbits of planets and stuff like that, but everything in the universe is an optimization of these two complementary components. So all structures and functions in the universe are optimizations of complementary components. I have a paper a month ago, reality is middle ground, okay? So, and the other thing is optimization for Maupertuis, obviously optimization of that planet orbit. There's a design to that orbit, and it has a character, that orbit. And for that orbit to stay regular, that optimization is like a solution to a problem. The problem is, how do I keep a planet in orbit around there, okay? And he says, well, God obviously did that, optimize it. But the thing I want to get is there's a teleos in there. So this is links to engineering. So when engineers make an optimization, they're actually, what leads them to try and optimize one way or another is whatever their purpose is, or whatever they think their purpose is. Okay, now here's where things got messy. This is going to go back to Schindler's thing. So there were two paths from Maupertuis. And Euler, who's like the genius of all mathematicians at the time and everything, and maybe had this before Maupertuis, he says, well, Maupertuis is right. Look at the orbits of the planets, principle of least action, the cycloid problem, all this stuff, really great. And then he says, he's correct, but it's not very useful. What? Why is it not very useful? Okay, so Lagrange and Euler go off on this thing, and they say, well, it's not very useful, so what we need to do is we need to do some idealizations. So you get the Lagrangian, analytical mechanics and so forth. And I'm going to explain to you what the problem is here. But the thing is to understand is Lagrange is deterministic ultimately, okay? So it's deterministic, and you have conservation. So one thing you want to know if this is a mechanical system, ask the question, is there a symmetry and is there conservation? And there's conservation in that, and there's conservation in Hamilton as well, although that's debatable a little bit. So the other path from Maupertuis is this guy Lazare Carnot. If you've never heard of Lazare Carnot, you will have heard of Lazare Carnot. He is the genius, the path less traveled I put down. So Lazare was one of the guys. He was Sadi Carnot's father. The real genius. Sadi is simply an application of what Lazare was doing. Now Lazare is an engineer. There's a whole bunch of them at the École Polytechnique, which is the first engineering university in Paris there, and. So he's got this thing which I'm involved in translating right now because it hasn't been translated, embarrassingly. And he says, here's how he sort of throws down the gauntlet. He says, everybody knows that there's a trade-off of velocity, time, and power. So how fast you want to do something, this is like engineering, like how fast do we want to get this done? So you can always do it. To accomplish something, you can do it different ways. And there's a trade-off in power, time, and velocity. And these just, and I would say every engineer knows this. Every engineer knows this. And I think every person walking around the world, commonsensically, tacitly knows that you can do things faster, slower. And he says no mechanics, none of these what they called rational mechanics at the time, no mechanics gives any account of this. I would take it a step further. The rational mechanics can't even make sense of the question because they don't have free will in it. They don't have options. Okay. So he says, I need to have a worldview in which this is true. I know how to do all these things. I have this mechanics, but it doesn't, determine me. So he has the thing, it's indeterminate and before you make a choice. So he has engineers in the world. He has nice relationships in the world, and he can act in the world. That's what he's going for. How do we get free will, if you like, and scientific determinism together? Put it that way. Now, there's this book out, which I highly recommend, Lazare and Sadi Carnot. and one of the discovered things. People want to leave or what? No?
Can I just point out we're over time for the session?
Yeah, okay.
So if you'd like to leave, you're welcome to leave. If you'd like to carry on and people would like to stay, there's no...
Absolutely. Okay, so I'll be 5, 10 minutes.
3:15 is the end. We were only in
How could you leave?
started.
Okay, so these are 3. Okay, good. So these are 3 of the publications that I'm working on to translate. These are some of the guys that hung out with Lazare. He's not an outsider, so to speak. And he wrote, one of the first things he wrote was this thing, a reflection of the metaphysical principles of infinitesimal calculus, or infinitesimal. And basically, somebody said it's a justification of the use of calculus. And what it is this is justifying what Lagrange and Hamilton are doing, and he's explaining why it's useful. If you have a world of complementary components, if you want to investigate this way, you have to dampen the other one. You have to find the static point of the other one, and then you could ignore it. Okay? And this is what went on in variational calculus and stuff. So I'll go fast through this. Anyway, so you can do all that stuff. So here's an example of this. So Pauli says this to Heisenberg, the same sort of thing. He says, look, he's working out the mathematics, which Heisenberg's not too good at. So Pauli works it out. He says, well, reporting back, he says, I can tell you one thing. You can observe, investigate, do things in the P way or in the Q way, but if you try and do P and Q together, it'd drive you crazy. Okay, it's the same thing that these guys are saying. In order to do useful things, in order to look at the world in a practical way where you're going to find these nice Cartesian relationships that you can work with, you need to dampen out one of them. Okay, you need to have a static point, an equilibrium point, which is what the whole principle of least action is about. So Bohr didn't miss this, in case you're wondering. This is Bohr's coat of arms. Across the top says contraries are complementary. Anyway, so what happened after Maupertuis? It went off on Lagrange and Hamilton. Very useful, okay? But they're both assuming that the world's mechanical. They're both assuming conservation of energy, and they're doing it. It's very useful because in the domain of validity that you're working in, that works and is great. I can do induction, I can do derivatives, I get great mathematics, but it's bounded, okay? So then something funny happened called quantum theory. And Planck comes up with this idea of action, the quantum of action. And Planck's concept of action is the same as Maupertuis. Okay? It's dualistic. It has particle aspect and a wave aspect. Okay? Now Einstein takes that. He actually understands it, I think, better than Planck did. He understands some of this stuff, and that's the foundation of both quantum theory and relativity. So the other thing about this is in mechanical systems are conserved, and if energy is conserved, it's sort of like saying action and reaction. What's the net change? Every action has equal opposite reaction. What's the net change? Zip, 0. Okay, so there's nothing changes. So these things, mechanical systems don't evolve. So the Big Bang was very embarrassing to these people. They do some hand waving and so forth stuff. But in engineering, engineering work always involves.
Please excuse me.
That's fine. Yeah, go ahead. Incommensurabilities and complementary aspects. So anytime we do work, there's always a loss, and the loss is incommensurable with the action. Okay, you can't recapture that loss to serve the project. Okay, because then you'd have perpetual work. So one of the consequences of this worldview is the world evolves naturally, automatically, because if the world is evolving thermodynamically, thermodynamics naturally evolves and generates itself. And so what's the net product of this? It's the universe. John Barrow wrote a great book called The Book of Nothing, which says if you take the mechanical view, add it all up together, well, you got nothing. Atkins says the same thing. He said if a sort of malevolent person would come along and say, great, you make mechanical universe, everything conserved? He says conserve nothing, because it all adds up to nothing. I'm going to go quick here. So the other thing is optimization, I think, is unique to engineering worldview and systems worldview. Optimization is only relevant when you have two incompatible points of view. Okay, in mechanics, there's only one point of view, one objective reality. That's it. Shut up and calculate. That was the answer. That was a lot of physicists after quantum theory came up. They said, "What about?" And they said, "Shut up and calculate." And if you go through the definition of your Lagrangian or your Hamiltonian, you're going through this series of choices to narrow it down. Say, okay, this is my system. Okay, and I can ignore that, and I can ignore that, and I can ignore that. Now it's deterministic. That's what you do in Lagrange and stuff. Okay, so again, pragmatism is a philosophy of engineering. I hope Jersey agrees with me on that. It's a participant thing, and basically what's embodied is this is the knowledge. Okay, knowledge is embodied. It's not just that we know things; that we do things with what we know. It's R, D, D, and D. Okay, and so evolution, Dewey called it the construction of the good. Okay, because we're trying to make the world better. This is saying optimization is good. So again, it went Lagrange, what Lagrange did, what Hamilton did, same stuff. There's a great book by a friend of mine called The Lazy Universe. It's a great introduction to the principle of least action. And one of the things that Jennifer points out is just like, okay, in Lagrange and Hamilton, one thing they don't deal with well is dissipation. Well, that's pretty straightforward because as long as my system's mechanical, then I don't have any dissipation. Okay, mechanical causality is like, there is no loss. Okay, if you have a system where loss is, not ignorable, then Lagrange and Hamilton don't work well, or at all. Okay, so we had these two paths. One went through Lagrange and Hamilton, the other one Carnot and Planck. Boom, boom, boom. Okay, so this is going to wrap this up here. So Atkins, who's one of my guru gods in all this sort of stuff, I took thermodynamics at Berkeley when I was doing physics, and I was taught that Boltzmann was right, and that's the right way to look at the world, and so I get and Carnot and is a sort of footnote of history, the caloric, and nice, put it in the history book somewhere. But if you actually look, I went and looked at like 8 textbooks in thermodynamics, trying to convince myself that Atkins was right, that there were 2 different versions of thermodynamics, and you find the ones that are dominated by the engineers, they do mention the physics one, but they say, well, the real one is engineering thermodynamics, and the physicists do the other. They mention the other one. So it has both aspects. So these 2 aspects are not compatible. So the engineering thermodynamics and the physics thermodynamics are not compatible. So the question becomes, what are they? Now, Atkins says, I think maybe they're complementary. This is sort of like open system, closed system thermodynamics. They're complementary. Not so much. I think actually that what I'm arguing is that engineering thermodynamics is actually the more general, and the physics thermodynamics is full of idealizations, and so engineering thermodynamics subsumes. Okay, so here's some rough conclusions of what I'm trying to say. So I want to say that systems theory is engineering is systems theory, systems engineering, and engineering is thermodynamics. Okay, they're all about thermodynamics. And systems engineering thermodynamics constitutes a more general framework that subsumes and supersedes all possible scientific mechanical worldviews. Systems engineering is self-referentially coherent, which scientific worldviews are not, and has a strong supportive relationship to quantum theory. The systems engineering thermodynamics worldview has inherent structure and function in it. One of the things about the engineering world, the engineering world has structure and function in it. Okay, you try and explain structure and function from a scientific foundation, all you get is like, oh, we got entropy, and like they don't have any structure and function. Where do we have stars and planets and all this stuff? They're dead. It's inherent to the scientific worldview that there's structure and function. Okay, which I could justify more. So the other thing that's important here for I think everybody, I would hope, is this point of view, whether or not you're buying into it right now, gives us a different way to approach a whole bunch of questions and problems that we have. Okay, which I'll, about there are problems in cosmology, there are problems in biological evolution, there are problems in economics. Reality has a history. Science, do scientists take history? No, they don't need history because the laws of the universe are universal. So if I can find the laws now, why do I have to look back? Wrong. Okay. Swillen has challenged this, a bunch of other physicists, but they don't go far enough. Also, engineering is naturally value involved. We've been having this C.P. Snow's thing, the scientific community, the humanities community, engineering, they're both the same thing. They're all together, not inseparable. So it unifies the superseding thing, brings the humanities in, gives them a good base, and humanities makes sense in an engineering framework. We want to explore possibilities, we want to understand justice, we want to know what ifs, all that stuff in literature and all the humanities, value questions, so forth, that all makes sense in the engineering worldview. It does not make any sense at all in the scientific worldview. So that's and of course the science, I'm saying, is also a part of the engineering worldview. It's compatible with that. So anyway, it's naturally valuable. It's trying to make the world better, and I think it enlightens engineering practice. I didn't go into too much, but it helps engineers understand what they're doing when they're optimizing and what optimization is involved in that. And to understand that, what they understand is that optimization questions are not analytically solvable, okay? I mean, you can go down, but you're always going to have to make idealization and compromises and so forth. So if I want to, anytime I'm doing an engineering project and I have, we're getting them into STEM now, and all these different perspectives, well, they're not compatible. Okay. Well, if you understand they're not compatible, then that gives you a thing. I have a whole bunch more on that, but I'm not going to do it. Anyway, so this is applicable to all this stuff. Here's a in case you get, so this is called the evolution. It's all about design. So this is evolution design. This is a front page of Harvard Business Review, okay, which I'm sure you all read. And the point is, what people are realizing, that some people say, well, engineers just do what the CEO tells them to do, or what the government tells them to do. Well, to some extent that's true up to a point, but the guy who's designing the corporation is also, that's a design question. Okay, how am I going to design my enterprise? How am I going to design? The economy? Do I like what Trump's doing with tariffs or not? I mean, these are design questions all the way up. Everything is a design question. Everything is a systems question. The worldview, the ultimate worldview, is a design question, is a design worldview, and that's the deal. So I could go on with stuff, but that's kind of that's good enough. Okay. And I'm happy to answer questions if anybody has any. Obviously, totally clear. Yeah.
The notion of that you made with optimization engineering.
Yes.
Would you say that you could have engineering without optimization?
No, that's kind of what Bill was trying to say. I mean, in other words, I think when you're doing in engineering, you always have trade-offs, and do it this way or that way, and what's the best way to do it. You're always confronted with that. I mean, that's just the basic. That's the basis of doing anything. I mean, I'm designing my life. How much time do I spend with my kids? How much time do I spend at the office? That's a design question. Okay. So anything that anybody is doing, if you're an engineer, everybody's an engineer. Everybody's an agent in the world. And you say, are they always facing optimization questions? Absolutely. Okay. You always have different ways of doing things. You have to make a choice. How do you choose? Make a judgment. Kant's third critique. You have to make a judgment. There are always alternative ways to do it. And one of the problems, I think, the idea that engineering is applied science, which is one of the things that Vincenti's trying to pose. We use science. Great. I mean, I want to know that the floor is there. I want to know when I walk on it. If I throw the ball, I want to know. Those are all scientific. But engineering is more than that. And action is more than that. And performance of work is more than that. You need a more sophisticated conceptual structure to understand that. And if the engineer understands himself in the bigger world, that's good. The problem, it's still going on. A lot of engineers are taught that they're just doing applied science. Okay. But what Vincenti's pointed out is you don't get an airplane from science. Okay. And you don't get any of these decisions from science. What we do in engineering many times, and this is what Lagrange and what Schindler is absolutely right, is what we actually do is we keep making these choices. We keep saying, well, I can't ignore that, but if I actually put it over here, then I can ignore the temperature question. So I can ignore that, and then I can do it here. Well, let's not make it that big. Let's make it smaller, then I'll have less noise. We're all doing these questions, and as we do that, we're designing our system. That's the design process. That's what we call iteration. And saying, well, oh, wait a minute, that's going to cost too much, or yeah, in this time frame, the NASA guy was saying, in this time frame, I don't have time to redesign that rocket engine, so I'm going to have to go with what I got. Those are all decisions that have to be made, and there's no analytical solution.
So in that sense, optimization would be temporal?
Would be what?
Time-based?
There's always a time component to it, sure. Historically, so, today I'll make one optimize one way, tomorrow another. Yeah, sure. It evolves, and you learn. The idea you learn. What